So let me switch to English and let me start from this photo. Efros-Shklovskii, two names, and on this photo you see me on the right side looking at screen, and Alex Efros at the left side, and this is photo around 2000, so 24 years ago, at the conference in Israel. And also here you see our book, where we summarize everything we did in Soviet Union before 1984. The book, English edition, comes from 84. It is available. So what I will be talking about as introduction follows this book. And if anybody is interested, this book, a good file of it, electronic file of it is available from my website, or if you request, I will send it to you. Okay. Now, let me start from very beginning. When I came to Yoffie Institute, everybody was dealing with semiconductors, germanium, silicon, gallium arsenide, and everybody was excited by Anderson's work. And let me start. Okay, so I'm still speaking Russian, yeah? Oh, I'm speaking English, I'm sorry. Okay, so I will start from Anderson. Before Anderson, everybody thought that if this is a semiconductor gap and we see donors, some of them populated by electrons, some of them empty, and they're empty because some electrons are gone to acceptors, and this is called compensation. If we deal with compensated semiconductor, nevertheless, everybody thought that all donors have the same energy, and because they have the same energy, they make a band, and states are delocalized. Phil Anderson said this is not correct, and because there are random potentials. Random potentials are coming from charged acceptors, negative, and from empty positive donors, and they move energies up and down, and as a result, there is a density of states are smeared by classical shift of energy of a donor. And that's how Anderson, and as a result, states of electrons on donors are localized. There is no impurity band as people were thinking, but there is a classical impurity band, as we called it, which means that there is a spread of energies, density of states, and that's it, and all states are localized. So that's Anderson's statement, 1958, all low density, at the low density, all donor states are localized. Well, immediately available was confirmation of this. This is Helmut Fritzsche, a good friend of mine, and discoverer of Hopin conductivity. So he dealt with this, he dealt with transport of electrons at donor impurity band, and he discovered that he saw that at large temperatures there is electrons are activated to conduction band, but at low temperatures this is T-1. So low temperatures on the right side. At low temperature, there is another activation energy, and there is a very small activation energy related to this spread of density of states of electrons. And he called this Hopin conductivity, and this is a classical presentation of Hopin conductivity. When I came to Yoffie Institute, one of my colleagues, Irina Nikolaevna Isievich, told me that you seemingly have interest in statistical things. So most disordered thing is this problem, and we don't understand, nobody understands how to solve it correctly, and you should do it. Well, I recalled this 3 years later and got excited about Hopin conductivity and worked on it. Now, by that time, Elihu Abrahams, another friend of mine, who died also in 2018, presented a picture from which we can start thinking about Hopin conductivity. This is called resistor network. So those are donors connected by resistors, and that resistors, each resistor corresponds to hopping between two donors, I and J, or I and J I have lower, sorry, I and J, and each resistance is some prefactor and some exponential factor, and an exponent we have two distances between two donors divided by Bohr radius, and this is related to hopping, small probability of hopping between two donors, and we have also energy activation, which is related to spread of states at a donor peak. And he presented this thing, this way of thinking, and I, myself and Efros, fully accommodated this way of thinking to Hopin conductivity. Well, this Hopin conductivity, which I am talking until now, is called nearest neighbor hopping. So electron hops between two nearest donors, and then with two nearest donors again and again. But and we figured out how one calculates very nearest neighbor hopping with percolation approach. I will not talk about this, and we thought that we understand everything. But then in 1969, I come to work and I see a paper from Neville Mott. Let me dwell a little bit about Neville Mott. I was lucky to meet with him several times. I will show later. I will show photos. He was my main hero. I always followed his steps, and when I became more confident, I always was correcting his mistakes. So one of major results which Mott came with 1969 was variable range hopping. Mott figured out that if temperature is very low, and this is density of states, that peak which I showed you in the beginning, but in a larger scale, so near Fermi level, this is Fermi level, density of states is constant, and as Mott thought, and everybody thought, and then instead of hopping to nearest neighbor, electrons can hop to distant neighbors. And Mott optimized that hopping, that variable range, that longer hop, and found that resistance which you get is prefactor times exponent, and then there is a T like Arrhenius, but not Arrhenius law, but with power 1/4, and T naught is some number divided by this is Boltzmann constant, and that's density of states at the Fermi level, and that's Bohr radius Q. This result was applied. Mott was thinking at that time about amorphous semiconductors. Amorphous semiconductors have such a almost constant density of states, a very small one in the middle of gap, and Fermi level, if it's not specially doped, sits in the middle of quasi-gap. And this is all happening in the middle of quasi-gap of amorphous semiconductor. And he invented this, he came with this idea, looking at experimental data, which already were showing such a behavior in amorphous semiconductor. This paper produced enormous response in community. There were thousands of papers or so, which, at least few hundreds papers, which confirm Mott's law. And in 1977, he gets a Nobel Prize together with Anderson, and one of the claims of Nobel Prize was variable range hopping. So, as I said, at some time, starting from actually 1973, I started to correct every his paper. And I got so confident that together with Efros in 1975, we destroyed major idea of his that density of states at the Fermi level is constant. Here, and we showed that actually at the Fermi level, there is a Coulomb gap of density of localized states, and it is illustrated in two cases. Sorry that here energy is vertical, and in these two plots, energy is horizontal. But you can figure this out. That's density of states at the as function of energy, and this is chemical potential, Fermi level, at in semiconductor with compensation, which is 0.5. 0.5 compensation means that you have twice two donors per one acceptor. So, half of donors are empty, half of donors are occupied, and Fermi level is between. This is occupied part of density of states. This is empty part of density of states. And this is what we called in 1975 Coulomb gap. We showed that that gap is parabolic in 3D. And this is a result of later computational numerical study. And this is chapter 14 of my book. Now here for illustration, another case is shown. This is a case which I mentioned of amorphous semiconductor. In amorphous semiconductor, we have conduction band, valence band, and we have a very small density of states in the middle. And this is Fermi level, exactly, or somewhere in the middle. And this is Coulomb gap near chemical potential. So that's our result of 75. Well, paper was written in 74, so it's 50 years. And that's what my paper about, the paper which Sergey found in archive and invited me to talk about it. Okay, so now I explained what Coulomb gap is, but I have to explain a little bit why it appears. And if anybody want to study this in more details, again, this is our book. Now, that paper about Coulomb gap of 75 was 3-page long and had few very simple equations. And the paper was discussing density of states, as I said, near Fermi level, mu, and the story is about Coulomb interaction of electrons at donors. So electrons in Mott case are not interacting. They just they just are in the random on random localized states, but not interacting when they sit next to each other. Here, interaction is important. So when we have interacting system, the only way to describe energies, you have to introduce them carefully. And this is energy to bring electron from infinity at the chemical potential to this side. And this side is empty because energy is above chemical potential. And this is energy to take which you have to spend to take electron from occupied state and put it at the Fermi level at large distance. That's definitions. And what we noticed, if we use this, and this is the only definition which is possible in the interacting system, we use these definitions, then we concentrated on energy which you pay to transfer electron from occupied state to empty state. And this all is happening in ground state of the system. So if I am taking electron from occupied state to empty state, I have to make positive work. Otherwise, this system is unstable. And so what I am presenting is, this is the first stability criterion, which now called Efros-Shklovskii criterion. And that's criterion and says that the energy which I spent on this transfer should be positive. But interestingly, it can be written like this. Ignore all these tildes. That just, I don't want to talk about this. So that's energies. And so, of course, if I transfer an electron, final energy is the J, and the initial energy is I. And so it should be difference between them. But there is also this term, which I call excitonic term. So we can use this terminology to, again, to recall Robert Soros. And this is excitonic term. And excitonic term means that if I'm transferring electron from here to here, and in ground state, energy of this electron which sits here is calculated when this guy is occupied by electron. But now, because I am transferring electron, this will be empty. And so there is attraction of electron which goes here to original state. And this attraction is Coulomb attraction. And this is minus E squared divided by the electric constant and Rij. And that's called excitonic term. And this makes the whole story non-trivial and leads to Coulomb gap. And how it leads to Coulomb gap? It says that electrons occupied and empty cannot be closed in energy if they are closed in space. Because if they are closed in space, Rij is small. Then this term is big, and this is negative. This is positive part. But if this part is smaller than this part, it will be negative. So then system will be unstable. So in ground state, it has to be stable, and it has to be bigger than zero. And that's the only thing we wrote and in this paper, non-trivial thing. So what happens from here is that for smaller, if I concentrate on a band of energies, here, if I concentrate on it, and I am calculating distance between I and J in this band, that distance should be so big that this is either zero or positive, and from this we can find Rij, and then we can find density of states from this condition. Density of states times distance, allowed distance for by band epsilon to power 3, and times energy should be order 1 or smaller. So our result is density of states is proportional to some coefficient, kappa cube, the electric constant cube, energy squared divided by e to 6. Remarkable expression, which is called Efros-Shklovskii Coulomb gap, and which is universal, depends only on the electric constant. And strictly speaking, this is inequality, which we prove. But we thought, and this was proven by numerics, is that if you model it numerically, you get this density of states. And this is because system is random and want to use every opportunity to reach maximum possible density of states. And if such density of states exists, parabolic, then picture is different from Mott. Mott was the constant density of states. Now it's parabolic, and you repeat now Mott's argument and optimization. And now I switched from Bohr radius to Xi, and because I copied this all from the book, and Xi is localization length, which in lightly doped semiconductor is Bohr radius. But if I come closer to metal-insulator transition, which we often think about, then it's larger. So it's either Bohr radius or larger near metal-insulator transition. Anyway, and our result is that the resistance as function of temperature is a new constant, which is now called Efros-Shklovskii temperature, which is just a Coulomb interaction at localization length, and this is some constant, and Boltzmann constant, and divided by T, and this is similar to Mott's, although TS is different, but to power 1/2. And that's what we had courage to publish in 1975 in 3-page paper, and we were waiting what happens. Now, I'll start. Well, it was many things happening, and this is what my talk devoted to his history. But I will start from experimental data, which confirm this law. And experimental data, probably there are acclaimed probably in 500 papers or so that they see this law. But for you, I collected only data which are which span or take dynamic range of resistances many orders of magnitude. For example, this is germanium and from Regensburg, and this is 6 orders of magnitude, where you see straight line resistance as function of T2 minus 1/2. T2 minus 1/2. Again, this is an exponent and resistance. So you plot logarithm of resistance and you plot T2 minus 1/2, and you have to have straight line. And you have straight line at 0 magnetic field. This is 0 magnetic field. Then he applies a magnetic field. He still has straight lines, but they are changing slope. And this is called magnetic resistance, and we will talk about this a little bit later. So I would like to concentrate on the magnetic field later. So now this is silicon, and my friend Dan McCammon from Wisconsin, 1993, 5 orders of magnitude, same plot, rho as function of T minus 1/2. Remarkably, that both papers for germanium and silicon are written by people who were interested in devices based on this law. When I was thinking about Hopin conductivity in Yoffe Institute, my friends were laughing. Everybody was doing lasers or something very spectacular, and say, "Why are you thinking about Hopin conductivity? Such a stupid thing, no applications." That's not exactly true today. Every good thing finds an application, and these 2 guys were working already on thermistors or bolometers or whatever you call them, thermometers based on this law. Currently, lots of studies of dark matter in mines are using silicon detectors based on this law for detecting WIMPs, dark matter, and lots of satellite devices for studying X-rays, gamma rays are based on this Efros-Shklovskii law. Both silicon and germanium is used by everybody, and so these guys came from this community, and they made fantastic achievement in experiment and pushed this thing very far. Now, those are conventional semiconductors, germanium and silicon, but simultaneously, similar physics works in granular systems. So this is magnetite granulars. You can see this is like nanocrystals. They are sitting in insulator, and they are conducting by hopping, and conducting by variable range hopping. So electron hops from here to here. Oh, sorry. This is old story. That paper is quite new, but I will show old paper next. And here again, you see, well, in this case, this is not resistance, but conductance. So it's sloping not up, but down. But otherwise, this is T minus 1/2, and this is conductance, and this is straight line. And this is 8 orders of magnitude change, and this law works perfectly. Now, the older paper, the granular nickel, this 73, and again, this is T minus 1/2, and that's nickel with in some insulator, and I forgot which insulator, and 8% of nickel, and particles are this size of particles, and 24 and 44, and depending on concentration of nickel and size of particles, you have different slopes. But all of them, 8 orders of magnitude, here show 1/2. And again, here it's resistance. So you have to get used. I will alternate from conductance to resistance quite often. And so slope is up or down, but it's still same straight line. So that theory, how theory works for granular system, was developed later by myself and coworkers. And one had to understand why these particles are charged in ground state, which is like donors charge in ground state, some of them, and acceptors. So why there are charges here? And charges here are because in the insulator, the localized states, and some of them are charged, and they induce in metallic particles. These particles are metallic. This is magnetite, and they induce image charges. And this, if say positive particle is here in the middle, it delegates fractional charges by fractional images to different particles. Each particle collects fractional images from many other charged particles in insulator. And as a result, they have random charges, and this is necessary to create Coulomb gap and to get such a curve. Now, last example to show how diverse are systems which show 1/2 is doped conducting polymers, and this paper 94, and here you see again conductivity, and so slopes are down, and always the horizontal axis is T minus 1/2, and conductivity is always in logarithmic scale, and you see perfect straight lines for 10 orders of magnitude of conductivity. And this is conducting polymers. Okay, so now I showed how spectacular results which are obtained for Efros-Shklovskii law, but still, like 30% of papers, or 20, claim that they see Mott's law. And that's very interesting that these two paradigms or two statements coexist for so many years, although equilibrium moved in my direction. As I said, like 70 to 30%, or 70 to 20%, 80 to 20%. But still, some cases you see Mott law. And where? First, if system has very low density of states, like amorphous semiconductor. And this is the where Mott applied his ideas, got his ideas, and this still is right. And why is it right? And this is right, I'm sorry. Because if you have very small density of states, this is density of states, this is energy. And then Coulomb gap, remember, Coulomb gap is universal. Universal law. And in 3D, it's parabolic. Well, I forgot to say that in 2D, in 2 dimensions, it's linear behavior. But in both cases, 2-dimensional and 3-dimensional, if you have Coulomb gap, you are supposed to have 1/2. But there are cases where you see 1/4. And now why? And because measurements in amorphous semiconductors are made at very high temperatures, around 100 K, and at that temperature, band of energies which Mott and myself and we talked about, that band of energies is wider than Coulomb gap, because Coulomb gap is universal. If density state is very small, it ends in energy very soon. And if ends at energy very soon, and band of energies used experimentally for that temperature is bigger, it's not important. And this is what happens in amorphous semiconductors. So this is one reason, and understood. Another reason is remember that Coulomb gap, both in 3D parabolic and in 2D linear, it is a result of Coulomb interaction. But in some cases, we have a gate, particularly in 2-dimensional cases, we often have a gate which is close to 2-dimensional system and screens Coulomb interaction. If there is a gate which screens Coulomb interaction, you are back to Mott, because Coulomb interaction is killed. So our achievement is about Coulomb interaction. And this was illustrated and confirmed in details by 2 experimental works. One of Arnie Dam in Case Northwestern in Cleveland in 98 on gallium arsenide, and one in graphene by Glatley in France. And what they do, and this is I'm showing data from gallium arsenide, 2-dimensional gas, dirty one, studied by Arnie Dam. And what we see here, and it is always like a rho, sorry, there is some power of t, but it's not very important, that's a prefactor. And again, rho is function of t minus 1/2. He sees lots of Efros-Shklovskii straight lines, and this parameter he changing is magnetic field. So in large magnetic field, he always sees Efros-Shklovskii 1/2. But when the magnetic field is smaller, and he sees transition to Mott. And why is this happening? Because there is a gate in this system, and when we apply strong magnetic field, wave functions of impurity in gallium arsenide, which are spherical, they are squeezed by magnetic field to cigar-shaped guy, and resistance increases, and hops happening at smaller distance, and that distance is smaller than distance to the gate, and therefore gate is not important, and you see Efros-Shklovskii. But when magnetic field gets smaller, you return to normal big wave function. Hops are longer, and when they are longer, gate plays the role. So this was illustrated, as I said, by Arnie Dam, and then by Christian Glatley for graphene in a new world based on graphene. So this is understood, and now I am showing again Mott, and now this is 1987, first time we meet Mott in person, and we are in Prague. So to the right, you see me on the left in blue shirt, and my friend Alex Efros on the right, and Mott, a little bit older than that photo was his Nobel Prize time, 1977, a little bit older. He is here is my age now, and for me, of course, it looked very old. And we meeting and discussing how we can, whether we understand each other completely and whether we agree. And it looks like Mott is signing a protocol of agreement, but that's of course I'm kidding. So by that time he agreed with us completely, and but this took 10 letters exchange from 1977, say, to 1987. 10 letters both ways. He was writing to us with questions, and we were writing with answers. And every letter would spend in every direction 2 or 3 months in KGB. And that's why every letter was taking him almost a year. So as I said, 10 years, 10 letters. But he got tired of this, and he decided that we should meet and think about this and discuss everything again. And he asked Maurice Rice to invite us to Zurich. Maurice Rice was director of Theoretical Physics Institute at ETH Zurich, and he invited both Mott and us, and we came there in 1988. First time going to West, and we spent 2 weeks talking to Mott. And Mott was taking one of us, every day for dinner. And this was happening because he had a Taylor Francis card, which allowed him to dine in any restaurant with a partner for the rest of his life. And this is for his service for Taylor Francis. And so he was choosing excellent restaurants in Zurich and explaining us what they're feeding us. And we haven't seen such dishes and everything, of course. And we have spectacular discussions with him about life and everything. And he was mostly worried about his ex-graduate student, Fuchs, who was a Russian spy in Los Alamos and who was a communist in his heart and volunteered to spy to Russians. And Mott wrote at some point recommendation letter to him. And then when Fuchs was released and he worked in DDR, he refused to meet him. And then Fuchs died. And he was traumatized. He loved Fuchs as a student. And he was traumatized by this story and was telling me every dinner whether I think he did right or wrong. And I was always trying to comfort him. But that's what stuck to my mind, every dinner. Anyway, as I said, Mott was always my hero and still is my hero. And he's fantastic guy. Now, well, that was nice story with Mott, but story with Anderson in the beginning was ugly. So Anderson was, of course, a leader of the field. And in 1978 and 1980, he writes papers with Fleischmann where he says that that Mott law is valid even with electron-electron interaction. So we screwed up. So that what follows from this, we screwed up, and Mott was right. And that looked traumatic. We looked at his papers. We thought this is nonsense, but we didn't write anything. And then in a couple of years, we see a paper from, by the way, you should recall that we were getting all papers of Israel like a year later or so. And so we kind of see what happens in the world in a retarded way. And that's maybe we could behave originally because we didn't know what the fashions are. Anyway, the paper comes from Morris Rice, the same guy who invited us later, and a new leader of disorder systems, Patrick Lee, and they repeated all our numerics and all our argument, and they declared that Efros-Shklovskii are right. So Patrick Lee worked together with Anderson in Bell Labs. He comes to Anderson and shows him his results and convinces Anderson that he was wrong. So Anderson takes it very seriously, and in Physics of Semiconductors conference in Montpellier in 1982, he goes and says that 4 Russians figured out all Coulomb interaction. He means Ronoff-Sugar for metals and Efros-Shklovskii for insulators, for Hopkin conductivity. And he said he was plain wrong. Efros-Shklovskii are right. Well, that's probably what made us famous. Now I'm switching to another chapter of this story, which is this same story in strong magnetic field. In strong magnetic field, beautiful paper is actually already in my book, Tokumoto, 1980. That's indium antimonide in N-type, as always strongly doped, because you cannot make lightly doped N-type indium antimonide because Bohr radius is 600 angstroms. And so if it is not no magnetic field, it's metal. But with the Planck magnetic field, you squeeze wave function like this, make Shiga type, and the wave function are not overlapping, and you get lightly doped semiconductor eventually. So from metal-insulator transition, increasing magnetic field, you get Efros-Shklovskii law at every magnetic field, straight line for many, many orders of magnitude. So it turns out that Coulomb in magnetic field, you have even better Efros-Shklovskii. And this is a paradox. And I realized this in 1982 when I come with this paper. Well, why is paradox? So if you have magnetic field which squeezes your wave function, hydrogen-like wave function, in a like Seeger shape wave function, in perpendicular to magnetic field direction, magnetic field squeezes, magnetic field is in this direction, it squeezes. In perpendicular direction, wave function decays as e to power minus rho squared divided by 4 lambda squared. See this expression? Sorry, should be here. Let's read of this, eh? Okay, sorry. See, that's how wave function behaves between 2 impurities. It's quadratic in distance. But in derivation of Efros-Shklovskii and Mott, we always assume that wave function decays linear in exponent. So in magnetic field, this is different law. If you recalculate Efros-Shklovskii in magnetic field, you get not 1/2 power, but 3/5 power. But experiment, as I showed, shows exactly 1/2 power. And so something is wrong in this simplistic argument. In 1982, I come into this explanation. What's wrong? When electron hops from one impurity to distant impurity, it sees other impurities on the way. And tunneling wave gets scattered by these impurities. And every time momentum is given to impurities, and this is virtual scattering of tunneling wave. And when momentum is given, you remember from Landau that center of Landau oscillator is shifted. If in the beginning, the center of Landau oscillator was here, after scattering it is here, after next scattering it is here, after next scattering it is here. And that's why wave function decays only as rho squared divided by 4 lambda squared, where lambda is magnetic length, only between 2. And if you want to calculate total decay from here to here, you get first power of total distance because it comes from number of scatterings, and you get first power. And if you get first power, original Efros-Shklovskii argument is correct, 1/2 is correct, and that's what you see in experiment. And dramatic information of this comes from quantum Hall effect. So in quantum Hall effect, as you know, conductivity as function of, or resistivity, both look similar, as function of filling factor nu has peaks at half integers, and between it has minima, and in minima sigma xx is supposed to be equal 0, but there is hopping, and Klitzing looks more carefully at the hopping behavior here at these filling factors, which are shown by thick lines. So he goes in minima, and several minima, and studies conductivity there. And his result again is T minus 1/2. And so in quantum Hall, in localized state, where localized states are important, between peaks of sigma xx or at plateau of sigma xy, conductivity sigma xx behaves according to Efros-Shklovskii. And he compares this with T minus 1/3, which Mott gives for 2D, and apparently we are much better. And that's another dramatic story, of course, which appreciated by everybody. And then it was repeated by many experiments in quantum Hall stories, and eventually even for fractional quantum Hall by Greg Bebinger in 1987. So everywhere in quantum Hall effect, where states are localized, Efros-Shklovskii wins. And we use that for prediction in 1983. In 1993, I'm sorry, with Polyakov, Dmitry Polyakov from Yofa Institute, who is now for many years in Karlsruhe, we claim that Efros-Shklovskii is valid everywhere where states are localized, and Efros-Shklovskii temperature is E squared, remember Coulomb expression, divided by the electric constant psi, and psi is localization length, and localization length diverges at half integers where we have peaks, and there's a divergence of this, and as a result, because it diverges, then T naught goes to 0, and we can find the width of the peak. The width of the peaks were measured as function of temperature by Dan Tsui, and remarkably showed a beautiful power law where this kappa is 0.4. And we showed that kappa is nothing else as 1 over gamma, and gamma was known by that time, and we explained this 0.4 law. And that's what we did with Polyakov, and the result is we said that Efros-Shklovskii, being the story about insulating states, determines width of the peaks. And also we extended this argument with with in other physics, that's that's the width of peaks as function of current which you derive in quantum Hall system. And we predicted that it should be power which is twice smaller than kappa. Kappa is 0.4, this power is 0.2. And again, Tsui and co-workers in dirty gallium arsenide, and then in very clean gallium arsenide, and then in gladly in graphene, they confirm our results. So I repeat, Efros-Shklovskii is valid everywhere in quantum Hall effect where states are localized. And end of Efros-Shklovskii predicts width of the peak, both as function of temperature and as a function of current. And of course, I want to show this picture, this photo. That's 1914, so 2014, in Florida at a conference, Strong Magnetic Field. Klaus von Klitzing, myself, and my wife Marina celebrating old stories. Klaus is a good friend, and he came to my birthday workshop this year, a week ago, and presented another beautiful talk. Of course, now he talks mostly about metrology. Now I'm talking about more complicated business. I still can use 5 minutes or so.
Yeah, sure. Yeah, sure. Please go.
Very interesting. So what we showed, I'm talking about 3D here, and I'm talking about metal-insulator transition. And so question is, what happens to Coulomb gap at metal-insulator transition? Does it survive it? Of course it doesn't, because on the other side of metal-insulator transition, we have metal, and in metal density of states is constant. There are small corrections, Runefeld-Scheuer corrections. I'm not talking about them. Okay, so how evolution from parabolic gap to a constant gap happening, and we came with a scaling conjecture or ansatz. I came with this ansatz, working together with experimentalists and my coworker Guyan, and it turns out that our ideas are very similar to what Macmillan had from metallic side of transition. So this is what's happening if I am going from insulator to metal. In insulator, Efros-Shklovskii parabola. Then I'm coming closer. Now parabola gets narrow. Why it gets narrow? Because we have the electric constant in a parabola. The electric constant here is kappa. And kappa grows near metal-insulator transition. Kappa to power 3 grows even faster. And so Coulomb gap becomes steeper and steeper when I approach transition from insulator. And that's a line with this line. Now, what happens at the transition? And conjecture is that at the transition, there is a dispersion of the electric constant as function of distance. And that's why it leads to Coulomb gap, which is square root, roughly. Well, it's index, but I'm just oversimplifying. It's like square root at the transition. So Coulomb gap, instead of being like this, becomes like this at the transition. Now, if I go beyond transition, the scaling picture shows that now on the other side, I have this kind of behaviors, and they start from this, then go like this, then go like this, and then go straight. And that's a scaling conjecture, and that was confirmed experimentally. Look at this. This is the same Mark Lee, his paper before me and paper together with me. And look at here. This is concentration of donors, which is 80% of critical, where you remember that if I have a semiconductor at some critical concentration, big concentration, the semiconductor becomes heavily doped and metallic. And that concentration is NC, and we are at 81%. Something like, and this is tunneling experiment, tunneling. And we see this tunneling density of states. It's like Efros-Shklovskii parabola. Now I'm coming closer, 86%. Gets steeper, see? Parabola gets steeper. And I see something here which is new. And then at 90%, even steeper. 95, I'm almost losing this parabolic part, and I have only square root. And then I have constant and square root and something like this. And now it's already 110% of critical. So that's experimental a confirmation of this story. Now, let me see how many. Okay, I'll skip some. Let me go through this story. So up to now, all this story was ohmic. So we were talking about ohmic conductivity. It's a very small electric field. But what happens if you take very small temperature, but large electric field? This is the picture drawn just for some density of states, which looks like exponential. Doesn't matter. So what happens if we have zero temperature? At zero temperature, you can only emit phonons. But if electric field is small, you cannot emit phonons. But if electric field is strong, and this is the line of potential created by electric field, linear, and you start with electron with this energy, and if you're tunneling, emitting very small phonon, then here, at some distance away from that point, the distance is x, you find yourself at energy EEx higher. And if you think a little bit, this corresponds to effective temperature, which works in this system. And that effective temperature is charge times localization length times electric field divided by 2. That's the whole idea belonged to Mott again in 1973. But he screwed up in finalizing and never reached to this. And again, as I said, this was first paper where I start correcting Mott, see one thing after another. And I corrected everything about strong electric field. I corrected Coulomb gap, and I corrected him in a high frequency absorption where I changed one power from his expression. I will not talk about this. So this is my achievements in straightening out Mott's results, but still he is my hero, and he was a leader of the whole field, created the whole field. Now, if temperature is like effective temperature is like this, you can put it instead of temperature in the denominator, and as a result, you have current as a function of electric field obeying this non-ohmic Efros-Shklovskii law. This law, and epsilon naught, is a constant times charge and the electric constant and localization length squared. And this law was observed by many people. I am not showing data. Data are usually shorter, not 8 orders of magnitude, by 4 orders of magnitude, which is decent enough in current. And most of interesting data recently were obtained in graphene oxide. Graphene oxide is what you get oxidizing graphene. I'll skip this, and I will. This probably will be my last view graph, but that's enormously complicated. But here I'm talking about screening of Coulomb gap. That's usually questions I get. Does Coulomb gap screen itself? That's a delicate question, and it took us from 1975 to 1984. Every day we come to work, we start from arguing how screening works. And for 9 years we were arguing with Efros until eventually in 1984 we made numerical experiment which clarified the story. And arguments are very interesting. So first, what if the density of states at the Fermi level is 0? This means that we are not supposed to have screening. But there is another picture, because screening radius always has density of states. And if density of states is 0, then it should be screened. But there is another picture. If Fermi level stays here and you move the density of states up and down, apparently you bring new electrons if you move it up. And so there is screening. And so there are several arguments against and for screening. And if screening exists, the whole thing is nonsense. And if screening doesn't, then why? And so we were arguing with Efros, taking sides. For 1 year, I'm on this side, another year, I'm on the other side, and we arguing and arguing, still arguing. Okay, so what happens? What's the truth? The truth is that Coulomb gap, in the sense we are discussing, is not screened. And it's not screened because the following. So so what screening means for us? The electrons are hopping between localized states, and suppose electron came from that state to this state. Now it came here, and this is like just coordinate, and electron came to this state. So it was empty state, now it's occupied state. So charge changed from positive to neutral. You can say that you get new charge here, new electron. So what's the response of the system? And that's what numerical calculation showed us what's happening. What's happening is like this. So how we studied this? And we put we made a sphere of localized states inside, and we bring inside the sphere a charge, and we see what happens on the other side. And every time we find ground state with our algorithm, running many times through stability criteria and recalculating all potential every time. So what happens? And this is what happens. In 50% of cases, nothing happens. The guy came, nothing happens. In other 50%, 25%, one guy moves. So this electron moves out of this electron. And in other 1/8 cases, in 12% cases, another guy moves. And so in some cases, you have chains of electrons which move one after another. And that's what the response of the system is. But this is not real screening, because naked potential, original potential, is 1/r. What will it be now? Well, it's potential will be of the same order, because cloud is not spherical. For real screening, you need spherical cloud. That's just a linear. And as a result, potential is of the same order, but can have a different sign. So locally, if your electron comes and other electrons respond, potential is of the same 1/r, and so Efros-Shklovskii argument is correct locally. But there are cases where so how can you return to what you know by screening? You know by screening, you cover potential. How do you return to you cover? For that, you have to make systems spherically symmetric. You have to study many realizations of this experiment, and we did. And then in one realization, I have chain in this direction. In another realization, I have chain in this direction. In another realization, I have no chain at all. So I have to average over all realizations, and this brings back Yukawa potential. So Yukawa is something average, but Efros-Shklovskii gap is local phenomenon. It happened due to interaction locally, and it has not. This Yukawa has nothing to do with this theory. But there is a case where it's not true. Imagine you have a microscopic semiconductor on the left side, and here there is electric field coming like this. And now electric field creates response in semiconductor, and somewhere I have good response, somewhere I have bad response. And if I average over the whole plane of capacitor, so to say, then I get normal screening with this density of states here. So I repeat, if I talking about macroscopic averaging and study problem where averaging is important, like screening of uniform field, then I get screening. If I deal locally, I have no screening. So everything is right, Efros-Shklovskii is right, and that was a most complicated problem we ever had in our life. So whether I explained it correctly, I don't know. And at that point, I say thank you. And if you want to learn more, go back to original to that written text. That written text has that paper, and that paper, which is only 10 pages, has 5 pages of references and 200 references, and it talks, summarizes history in more careful way. I forgot to say that that file which I was showing you is based on my talk, which I gave in American Physical Society March meeting in March of 2019, on occasion of giving myself, Efros, and Abrahams. Remember Abrahams, who invented resistor network? 3 of us got Buckley Prize in 2019. And sorry, Abrahams died the same year, couldn't come. And Efros didn't come. And I was, it was only myself, the youngest one, who talked. And the talk I presented was roughly the same talk you had, with some additions. Thank you for listening.
Да. Спасибо большое, Борис Иванович. Очень интересно. Спасибо огромное. Друзья, если у нас есть вопросы, то, пожалуйста, можно или поднимать руку, или потихонечку, может быть, включать микрофоны, пробовать, ну, так, чтобы мешанины не было только. Или можно написать в чате. Да, пожалуйста,
Гриша.
Григорий Максович Миньков.
Добрый день. Скажите, пожалуйста, а вы не привели никаких результатов относительно частотной зависимости проводимости в этом режиме?
У меня есть слайд, если я его сейчас выковырю для вас. Я просто мог про все сказать, да. Частотной зависимости.
Я понимаю.
Сейчас, sorry, я его найду. Вот он. That's microwave conductivity, Mott 71 and Brzezinski 73. They showed that, well, let me explain what Grisha asked. That's if you have a system or, localized states, and you you study conductivity at finite frequency. And Mott said that that conductivity should be proportional to omega squared. And Brzezinski and everybody, and Bert Halpern, everybody got omega squared. And we looked at this carefully, took it into account Coulomb interaction, and showed that 1 power of h omega should be replaced by this sum, E squared over kappa and R omega. R omega is this distance at which splitting between 2 donor states is equal to h omega, splitting due to overlap. That's a small distance relatively, and that's a big energy. And in many cases, this energy is bigger than h omega. And this changes, R omega is only a logarithmic function of omega. So this changes dependence from omega squared to omega. And this was confirmed by many papers. This all is discussed in detail in this paper, in a paper on archive, which I'm talking about half century. So that story is discussed there. All references to experimental papers which confirm this plainly, even in the cases where you have transition between these two regimes, so this is all confirmed, and that's another story where I was correcting Mott. And again, he's a genius, and he is a leader.
Хорошо, спасибо. Валерий Владимирович Вальков.
Спасибо за очень интересный рассказ. Мой вопрос связан вот с чем. Когда вот рассматриваются вот эти примеси, то примесная система, скажем, этих центров, там, допированных центров, она характеризуется там средними моментами. Ну, а дальше еще вот как функция распределения у нее есть, корреляционные характеристики. Вот
Сейчас
в этой
момент.
связи либо я...
Что вы имеете в виду под моментами?
Ну, вот, скажем, у нас есть случайная среда, это разбросанные примеси. Ну, и, соответственно, там будут, ну, скажем, средние характеристики, это говорят, первый момент, и потом более сложно, это корреляционная, там, скажем, корреляционный радиус случайной величины, ну и так далее. Может быть, я пропустил, у меня мой вопрос вот с чем связан. Так, физически вы совершенно доходчиво и прозрачно рассказали о происхождении щелей за счет примесей. Ну, она, значит, есть там физика Мott-Хаббардовская, и она теперь, еще навеяна вот этими случайностями. Так вот, мой вопрос вот в чем заключается. Вот полученные ответы, они зависят только вот от этих первых усредненных как-то характеристик это случайной величины, случайной функции, либо, вот казалось бы, должно быть и связь с корреляционной длиной. И, соответственно, должен быть разный режим, скажем, при рассеянии электронов, когда длина волны много меньше корреляционную или много больше. Так вот, поясните, пожалуйста, чего здесь я не понимаю?
Я не понимаю, кто
Мой
такой,
вопрос непонятен.
моменты чего, я не понимаю, поэтому я не знаю, что вам сказать на этот вопрос. Может быть, вы просто мне напишите, и я с удовольствием вам отвечу, но вы только должны определить или прислать
Ну
статью.
хорошо, если позволите, вот тогда второй вопрос. Вот, вот экспериментально на сегодняшний день, может быть, раньше-то не было, а сейчас более тонкие эксперименты, скажем, в случайных средах, зависимость сопротивления от направления было обнаружено или нет?
Что значит,
Ну,
если
скажем,
система имеет,
вот
дайте я...
пусть случайность.
Забудем про сильное электрическое поле. Вернемся к закону Ома, правильно? Да? Мы сейчас говорим про закон Ома. Теперь, бывает ли анизотерапия? Да, бывает. Бывают ситуации, когда, например, в полупроводниках у вас волновые функции анизотропны. Например, в strong magnetic field. In strong magnetic field волновые функции in gallium arsenide or indium antimonide, they are like sugar shape. We just discussed it, right? Sugar shape. So, of course, this direction and this direction, along magnetic field and perpendicular magnetic field, are different directions. Hoping conductivity depends on direction. But in my book, in chapter 6 and 7, I address anisotropy and calculate it. And that anisotropy is not exponential. It's a power law anisotropy. It was measured even at that time and studied even in that time, and experimental data are quoted there, and around hundreds of data, currently, of course, yeah. So that question is studied. Anisotropy can come from magnetic field. Anisotropy can come from, say, you take germanium and type, you have ellipsoids, and then you apply pressure, some axis. Some ellipsoids go down, some ellipsoids go up, and these ellipsoids who are going down are anisotropic, and they provide anisotropy. Same in silicon. So that's a very old story, very well studied. I'm not sure.
Хорошо,
Понятно.
спасибо.
Подожди,
Спасибо, Александр.
можно еще, как раз это как бы первая половина. Если ответ вот этот положительный, то есть есть эффекты соответствующие, то тогда вот возникает следующая проблема. В кристаллической среде, где есть кристаллические поля, и пусть даже это случайные разбросанные примеси, то вот как раз возвращаясь к моему первому вопросу, там как раз тогда вот корреляционные функции, они будут зависеть от направления, то есть вот как расположены примеси друг относительно друга, она будет зависеть разное по отношению к направлению кристаллографических осей. И это будет, как раз и источником возникновения магнитосопротивления вот даже в такой среде, где, казалось бы, пусть, с точки зрения первых моментов, среда изотропная, случайная, но изотропная. Вот такого типа-то еще, по-видимому, исследования не проводились.
Я не совсем понял опять вопрос. Я думаю, что если вы говорите о мезоскопической системе, а маленькой, конечно, есть анизотерапия, все там, маленькая система не самоусредняет. Но если вы хотите говорить о большом кристалле, то вот все такие случаи, которые я знаю, где волновые функции либо изотропны, либо эллипсоиды, которые проводят анизотропию в среднем, в кубическом кристалле, скажем, они макроскопически они изотропны. Это потому что тензор проводимости, он тензор второго ранга, и поэтому как только вы имеете дело с макроскопическим и с высокой симметрией, conductivity...
Нет, это все правильно, это так и будет.
Да, я думаю, что это лучше, наверное, уже в переписке обсудить, если можно.
Да, я приветствую и буду и вам отвечу, если только вы дадите достаточно информации, чтобы понять, что вы говорите.
Ну, спасибо.
Ага, хорошо, спасибо большое.
Боря, вот можно еще
да,
один вопрос?
Александрович.
Хотя, конечно, об этом речь немножко шла. Я понимаю, что последовательной теории тут нет, но все-таки, что говорит внутренний голос, внутреннее убеждение? Все-таки птичка Аронова-Альтшулера в точке перехода и ниже металл-диэлектрик переходит в кулоновскую щель? Это непрерывный процесс?
Этому мы посвятили с Альтшулером несколько лет, может быть, или там пару лет, или сколько, я не помню. И никогда не смогли ничего убедительного сделать. И мое мнение сейчас, что нет, что это другое явление. Там играет роль скрининг. И то есть это явление, которое и все было вычислено с учетом скрининга. И поэтому скрининг здесь разрушается. И как...
В диэлектрике
Да, я забыл, наверное, сказать. Что?
В диэлектрике скрининг разрушается. Конечно.
Да. И это не было никогда учтено там. И поэтому те вычисления на том уровне, которым они были сделаны, не переходят сюда. Но нам почему-то даже, хотя мы с ним работали и дружили, вместе, и, как вы знаете, у нас эти работы есть по level repulsion и так далее, мы не смогли ничего разумного сделать. И я не могу даже сейчас объяснить, почему. Осталось у меня понимание с 99-го года, когда я занимался вот этим вопросом, эта статья, вот, когда вообще-то вот эту картинку, что происходит на переходе, я придумал в 80-м году еще. Но с 80-го до 99-го, 19 лет, я боялся что-то сказать. Наконец, в 99-м году я обнаглел и написал вот эту статью с экспериментаторами. Но это все такое conjecture и абзац, или как вы хотите назвать. Никогда ничего строго не было сделано с металлической стороны. Кстати, вот вы спрашиваете, с металлической стороны, как это идет.
Да.
Я верю, что все, что сказал Макмиллан, правда про металлическую сторону. И это совершенно согласуется с моей гипотезой. Вот Макмиллан переходит в нас, это одно и то же. Но Аронов и Альтшулер нет. Теперь Макмиллан, и это замечательная история, был... Сейчас я на каком языке говорю, я уже забыл. Да,
На русском.
Сейчас. Sorry. То же самое происходит везде, потому что... Ну, хорошо. Макмиллан был критизован. He was criticized by Patrick Lee. And Patrick Lee said essentially that all states are screened and he shouldn't talk about Coulomb interaction. But in my paper of 1999 with experimentalists, I criticized Patrick back. And I'm saying that Patrick was wrong and Macmillan is right. And this I said on the grounds of that experiment with of 84, which I was talking about here. Yes, which I was talking on the ground of this, and because indeed there is no screening as Patrick. So Patrick essentially took this picture. He said, "Oh, we need for screening, we need thermodynamic density of state. Thermodynamic density of state is not density of state at the Fermi level, but it is then d mu gn or whatever." So it happened, thermodynamic density of states is what you get if you move up the whole distribution and get more electrons. But I said that's correct only for macroscopic object and uniform electric field. That's not correct locally. So that's my objection to Patrick Lee. Patrick Lee wrote this in review with Ramakrishna. And so I disagree with everything written there about Macmillan. And Macmillan is right. And Macmillan took into account destruction of screening and absence of it. And in this sense, Macmillan is a real guy with whom we are in contact. And I think there is a gap where we cannot extrapolate Aronov and Schuller in our direction, but we should look at Macmillan. That's my point of view. And it's in arrogant way expressed in 1999, but nothing is proven. But as you said, talking from bottom of your heart, that's what I said.
Хорошо, спасибо.
No development since.
No development since, except two theoretical papers, which seemingly confirm what I said about us and Macmillan. These two papers, the references are there, and probably references are even here. And that's one paper is Kravtsov and Marcus Miller, and another paper is Mirlin's group. And both papers, to the extent I understand them, they're really theoretical papers, and I'm not a real theorist. As recently Sasha Migdal called me, I'm a general physicist. And these two theoretical papers are seemingly agree with me, and when I discuss with authors, and I repeat, this is Mirny and Gorny, and I discussed with Gorny, with whom we are from both from Yofa Institute and understand each other perfectly, and another group is Kravtsov and Marcus Merler, and they, as far as I understand them, they agree with me and Macmillan. Okay, so that's probably all I recall. But if you want to deeper question me or particular questions, I will respond to you in email or Zoom or Skype.